In this video, we'll calculate the standard deviation for a couple of small examples. So we saw in the previous video that the standard deviation of a set of data is given by the formula square root of the sum of each data value minus the mean squared divided by n minus 1. And again, n is the sample size. X bar is the sample mean, and little x stands for each individual data value. So let's calculate the standard deviation. For this example, the weights of 6 randomly selected beagles visiting the vet in pounds. As we see in the formula above, the formula for the standard deviation needs the sample mean. And so in this case, the sample mean x bar, if it's not given to us, we can calculate it. So if you do calculate it, you'll find that it's 25.8, or actually 25.83333 repeating. So we could have also used 25.83, but I'd say rounding to just the nearest decimal point in this case is okay. So we're going to use the sample mean is 25.8. Again, you can calculate that to verify. So to calculate the sample mean, you would be adding up these 6 data values and dividing by 6 the total number of data values. Okay, so to find the standard deviation, my first step, if I'm doing this by hand, is to add together the squared differences. So add together each data value minus the sample mean squared, and add those values together. So in this case, that would be 24 minus 25.8 squared plus 29 minus 25.8 squared plus 20 minus 25.8 squared plus 24 minus 25.8 squared plus 31 minus 25.8 squared plus 27 minus 25.8 squared. So we're going to add together each of those values and find the sum. At this point, I would recommend using, some kind of technology calculator. I would recommend using, you could either use a calculator, or you could download an app on your phone that works as a calculator, or you could even use your web browser. So if you type in, 1 minus 2 or something in your web browser, Google will show a pretty decent scientific calculator that you can just use from your web browser. So all of those are options. So when you simplify each of those values, you will get 3.24 plus 10.24 plus 33.64 plus 3.24 plus 27.04 plus 1.44. So those are those 6 squared differences between the data value and the mean, and then you can add those 6 data values up together and you'll get 78.84. So 78.84 is the sum of the squared differences. So you can then find this value divided by n minus 1. So the sum of the squared differences divided by n minus 1. And remember, n is the sample size, and in our case, the sample size is 6. So the sum of the squared differences divided by the sample size minus 1 is 78.84 divided by 6 minus 1 divided by 5. And so in our case, that's 15.768. And our very last step is to just square root the whole thing. So square root of sum of each data value minus the mean squared divided by n minus 1 is equal to in our case, the square root of 15.768. And when we square root that, we will get 3.97. So our standard deviation, 3.97 for this set of data. Okay, now I'd like you to try an example. So I'd like you to calculate the standard deviation for the following set of data. This weights of 5 randomly selected dogs visiting the vet. So we have those 5 weights in pounds. Just so that we're all using the same amount of rounding, the sample mean in this case is 27.4. You can verify that by adding those 5 data values together and dividing by the number of values, dividing by 5. But that's what we will use. So again, we want to use that same formula we've been using, that the standard deviation is equal to the square root of the sum of each data value minus the mean squared divided by n minus 1. And so give that a try. Before you calculate it, though, I'd also like you just to think for a moment, will the standard deviation in this example be larger or smaller than the standard deviation in the example that we just did? And why would that be the case? So think about that and try calculating that out, and we will do it out together in just a moment. Okay, so first of all, what do we expect about the comparison of the standard deviations here? This data is more spread out than the data above, and we know that the standard deviation specifically is the amount the data varies from the mean. So here we have a sample mean of 27.4, and we see that the actual data values themselves are much farther away from the mean than they were in the previous example. So we expect this will have a larger standard deviation than the example above. All right, so now let's actually go ahead and calculate it. So our formula S for the standard deviation is the square root of the sum of each data value minus the mean squared divided by n minus 1, where n is the sample size. So first we could find the sum of each data value minus the mean squared. And so in our case, that would be 26 minus 27.4 squared. We're using this as the mean, which again you can calculate separately to verify if you wish, plus the next data value, 34 minus 27.4 squared, plus 6 minus 27.4 squared, plus 11 minus 27.4 squared, plus 60 minus 27.4 squared. So we are calculating that. I would again pull out some kind of technology to help you out at that point. And so when you simplify these, you will find these values as 1.96 plus 43.56 plus 457.96 plus 268.96 plus 1062.76. And when you add those values together, you'll get 1835.2. So those are the sum of the squared differences. So we now take the sum of those squared differences of the data value minus the mean and divide by n minus 1, where n is the sample size. So the sample size in this case there were 5 values, so the sample size is 5, and so we are taking what we calculated above, 1835.2 divided by 5 minus 1 divided by 4, and we get 458.8 when we finish that division. Finally, our last step, so this was step 2, our last step is to take the square root of that, and S, the standard deviation, will be the square root of, just writing the formula again, each data value minus the mean squared divided by n minus 1, the sample size minus 1, which is the square root of 458.8, and so that is 21.42. So our standard deviation S is 21.42, and we can compare with previous example, and for that, for the beagles, the standard deviation was 3.97, whereas this is for weights of random dogs of unspecified breeds. This makes sense that this is a larger value in context, because we'd expect the weights of random dogs of unspecified breeds to have more variation than the weights for dogs of a specific breed. So this value is smaller because the data values were closer together, and this standard deviation is larger because those data values were more spread farther apart. So we're going to wrap up this video by talking briefly about variance. Variance is another measure of how spread out data is, or a set of data is, and it is very closely related to the standard deviation. So the variance is just the square of the standard deviation, and conversely, the standard deviation is the square root of the variance. So therefore, the notation for variance is very similar. We know that, so for a sample and for a population, we saw that the sample standard deviation was given by S, and a population standard deviation was given by sigma. So this is for standard deviation. Based on this relationship between standard deviation and variance, so this was the standard deviation for a sample and a population. Based on that relationship, the notation for a sample variance is S squared, and the notation for a population variance is sigma squared. So this is the variance for a sample and for a population. So that is the notation, so definitely lets you help remember. And if we just think about the formula would be basically just the formula that we have for standard deviation, but we don't have to square root. So the formula for the for the sample standard deviation would be the sum of each data value minus the mean squared divided by the sample size minus 1. And note, this is just the formula for the standard deviation, formula for sample standard deviation S without the square root, because not doing this, because square root and square are inverse operations of each other. So before we take the square root, we have its square. And if we think about the examples above, then for the beagles, we would just, to find the standard, to find the variance, that would be the standard deviation, which we calculated as 3.97 squared. So we can square that value, and squaring that value gives us 15.76. So that is the variance, 15.76. And if you look back, this is the same as value in the second to last step of calculating the standard deviation. So it's what you get before you take the square root in the last step, which of course makes sense, again, because square and square root are inverses of each other. And similarly, for the dogs of assorted breeds, or the dogs with no specified breed, the standard deviation was, our standard deviation was 21.42. But if we square that, that will give us the variance. And so that would give us a variance of 458.8. So it's just the value that we get before we take the square root in calculating the standard deviation. So again, this is the variance. So this is not really a very different measure of variation. Basically, if all mathematics had been developed by one set of people, probably these two different measurements would not exist. We'd just have one or the other and use it consistently. But because different people kind of advanced the field of statistics, some people advanced it using standard deviation and some people advanced it using variance. And so depending on what particular thing you're doing, it might be more common to use the standard deviation or the variance, but there's no new information. If you know the standard deviation, you kind of immediately know the variance and vice versa. So they're sort of repetitive, but it's really good to know both terms because, as I said, some statistical softwares or circumstances will use variance and others will use standard deviation. We will mostly use standard deviation, but it's also good to know what variance is. So it's good to know what the variance is. So on a homework or quiz or something like that, I might at some point just ask you, here's the standard deviation, what is the variance? Or here is the variance, what is the standard deviation? So good to know what the variance is and its relationship between the standard deviation